All right, everyone, Mrs. Basega here. This is the 5480 Unit 4 Work and Power Review Assignment. For this assignment, I want you to do this whole thing first, then check the answer key, then watch this video. Don't watch this video unless you've tried it yourself first, because physics is all about practice. So to start off, if the sign of work is negative, that means the force and distance are in opposite directions. Remember this picture where if the force and the distance are in opposite directions, that means that they're going to cancel each other out. So the work done is negative. All right, so number 2, let's talk about work. Work is the change in energy, and change in energy can occur when an object is speeding up or slowing down, going uphill or downhill. So let's see which of those works. In A, the parachute slows the person down. That means their kinetic energy starts large and ends small. There must be negative work done in A because the kinetic energy is decreasing. But for B, the sled is not moving. Friction prevents the sled from sliding, so there's no energy before or after. The force of gravity acts on a bowling ball as it rolls down the lane. Well, remember, if gravity is acting down and the distance it travels is to the right, these two are perpendicular, so it can't be C either. That leaves A. The parachute is slowing them down, so there's negative work done by air resistance that lowers the kinetic energy. When something does negative work, the kinetic energy transforms to heat. So let's say that I have my car moving down the street and it has kinetic energy to start. Afterwards, it will have stopped. The kinetic energy of this car has negative work. It lost that energy and it turns it to heat. For number 4, I have 2 objects, right? Object 1 and object 2. Object 1 is 3 meters and 4 kilograms. So if I do PEG, that's 3 times 4 times 9.8, or 12 times 9.8. For object 2, this would be MGH, or 2 times 6 times 9.8. And hey, I don't even need to plug this into my calculator. Both objects have the same gravitational potential because if I calculate MGH for either, they both end up with 12 times 9.8. I didn't even need to get my calculator out. Sorry this picture didn't come out. It shows up great on the PDF, but it doesn't show up great on the printed copy. This has force on the y-axis and time on the x-axis, or sorry, displacement on the x-axis. So when is more work done? Is it done from 0 to 5? That's this section. 5 to 8, that's this section. Or are they the same? Just eyeballing this, from 0 to 5 has the larger area under the curve than from 5 to 8. So if I look as work is the area under the curve of force times distance, in this case, it would have more area under the curve from 0 to 5 than 5 to 8. In total, if I want to calculate this out, I would be doing 1/2 base height of this triangle. So it's a base of 8 meters, a height of, this says 5, it's hard to read, sorry about that, height of 5 meters. So 1/2 times 8 is 4. 4 times 5 is 20. There's 20 joules of work, and I did that by area under the curve of a force distance graph. Power is work divided out by the time. The work is 20. The time is 10 seconds. So it's 20 divided by 10, that's 2 watts. Watts are joules per second. So 7 is C, 2 watts. For number 8, calculate the gravitational potential energy. That's MGH. This is a 300 kilogram lift chair. The gravitational field of the Earth is always 9.8, and it goes 50 meters above the ground. This angle is irrelevant. I only need to know that this height is 50. So substituting that into my calculator, that would be 300 times 9.8 times 50, or, oh gosh, big number, 147,000 joules. Expect some big numbers if you're dealing with big masses. Power. Power is work divided out by the time. The work done is 147,000 joules. And hey, where do I get that from? I get that from the energy. Remember work energy theorem. If I took my object and I sent it up the hill, it started with 0 potential energy and ended with 147,000. So how much work occurred? Work must also be 147,000. The work is done by the motor, and that adds energy to the ski lift chair and Earth system. Work added energy, so if they're added 147,000 joules of potential, there must have also been 147,000 joules of work. Divided out by the time, 2 minutes of time is 120 seconds. So I needed to convert that into seconds. Be super careful in case I am a tricky one. So that means 147,000 divided by 120 seconds. That's 1,225 watts. Watts are joules per second. The closest one to this is B. And you know what? You get B for this if you use G as 9.8. Number 10, if you took the time as twice as long, if I made T larger, I would be dividing by a larger number. That would make the power smaller. The only one that says the power is smaller is C. Power and time are inversely related. So the more time something takes, the less power it requires. It's kind of like running slowly instead of quickly. If I take more time to run a mile, it requires less power for me to do so. This energy transformation, it says that the constant speed up here, so I need something where the kinetic energy does not change. So it can't be A. It could be B or C. For B, increasing gravitational potential energy because it's going uphill. And it can't be C because C says the gravitational potential energy stays constant. And it doesn't. It increases. Moving right along to kinetic energy. The larger the speed, the more kinetic energy something has. And when given a choice between mass and speed, speed generally dominates because speed is squared in the kinetic energy equation. So I'm going to quickly proportions all of these. If I do 3 times the mass, that would give me 3 times the kinetic energy. But if I triple the mass and double the speed, that's 3 times 2 squared. 3 times 4 is 12 times the energy. All right, what about C? What if I double the mass and triple the speed? That would be 2 times 3 squared, or 2 times 9. That is 18 times bigger. And finally, what if I leave the mass the same and quadruple the speed? That would be 1 times 4 squared. 4 squared is 16. So the one that gives the largest proportion is C. Because of its square, this gives more energy than the other choices. Number 13, if the mass of the object is cut in half and the velocity is doubled to 2v, what is the new kinetic energy? So let's do this. cutting in half the mass would cut in half the energy. Doubling the velocity would quadruple the energy. So 1/2 times 4, because think of this as like 2 squared to distribute this squared. 1/2 times 4, this kinetic energy would be twice as big. Kinetic energy and speed are a squared relationship, and that looks like a parabola. The more speed there is, the more kinetic energy there is, and since it's v squared, my relationship is an upward-facing parabolic curve. Now, the last parts are all about springs. This spring has increasing displacement, so I want you to think it gets stretched farther and farther and farther from rest. And the more you stretch it, the larger the force is. So what's one thing that says more displacement, more force? This is a direct relationship, right? If distance goes up, force goes up. It has a 0 that goes through the origin. So it's not a constant force. Constant force would look like that. It's not that. Does not change. Hey, does not change and constant force are the same thing. It's got to be A. Now, how do I calculate work from a force distance graph? Is area under the curve. So I'm going to do this area under the curve. That's 1/2 base height with a base of 5 centimeters and a height of, oh gosh, that looks like 3 newtons. So this is 2.5 times 3, or 7.5. Look at my units for a second. I'm going to leave this in centimeters because it's in centimeters already. So newtons times centimeters. This is a non-standard unit for energy, but it makes it easier than converting. So let's just leave it for now. I left it as centimeters, so I don't need to convert. Now I'm going to do the same thing. Now, if I move this up to 10, this new triangle has a base of 10 centimeters and a height of 6 newtons. So that's 5 times 6, or 30 Newton centimeters. Beautiful. Now, when we stretch the spring, we're doing work. So let's say this is a person, they're doing an applied force. We stretch the spring and we do work. That work adds spring potential energy, and it adds it in an exactly equal amount. Because think of it like this. If there's no energy to start, and here's you coming along and doing positive work to it, you stretch the spring, you add spring potential energy. If you added 30 Newton centimeters of energy, there would be 30 Newton centimeters of spring potential energy because all the others are 0 in this scenario. No kinetic, no gravity, just springs were cool. So the spring Earth system gained the 30 Newton centimeters of work you put in. 30 equals 30. Work is equal to the change in energy. For number 19, when the spring is stretched to 5 centimeters and stores energy, that's less than if the string is stretched to 10 centimeters and stored energy. When it's stretched to 5 centimeters, it stored 7.5 Newton centimeters. When it's stretched 10 centimeters, it stored 30 Newton centimeters of energy. And when I look at these two numbers to compare them, they're not the same. They're not the same amount of energy, but they're not double either. If you calculator this out for me, 30 divided by 7.5 is 4. When you double the distance, you also double the force. Think of it as you double both the base and the height of this triangle. Doubling and doubling is quadrupling. So by doubling the displacement, you actually get 4 times the amount of spring potential energy. That's not a direct relationship. Roller coaster. Let's say that this is frictionless. This is a conservation of energy problem. There is no work done at any point during this roller coaster ride. So at A, it would have all the gravitational potential energy. At B and E, it would have no gravitational potential energy. C is a little bit higher, so a little more energy than D. Gravitational potential energy is based on height. This equation says if there's more height, there's more PEG. So A has all gravitational potential energy. But conservation of energy means that if our roller coaster is moving about here, and it all starts with the same energy, if A has large potential energy, it must have small kinetic energy. If E has low potential energy, it must have large kinetic energy. That's not precisely, but close to an inverse relationship. That's why these orders are reversed. B and, oh, that's supposed to be an E, my bad. B and E are at the same height, so they have the same potential energy. So they have the same kinetic energy. A is highest above the ground, so it has the least kinetic, more potential. B and E are low to the ground, so they have low potential, high kinetic. If friction were to be included, B occurs earlier in time. Since friction takes time to take away energy from the system and B occurs earlier, B would have more energy and E would be slower. If you lose energy over time, the one that's earlier in the timeline is the one that has more of its energy still intact. So it goes faster at B. Now, Lucy's out here doing pull-ups. She starts at the ground. She is at rest at the reference line. So let's call this zeros. Then she does a pull-up. And since we assume she does constant velocity, you can kind of ignore any velocity terms here. She does this work to lift her body, and in lifting her body, she adds gravitational potential energy. Her applied force is upward, and she moved her body upward. So work was done by the applied force, it was positive energy, and it added gravitational potential energy to the system. To calculate the work, I can see that she gained gravitational potential. So if you're looking at this and you're like, but Miss Besega, you said work, why are you doing PEG? Well, I'm doing it because whatever PEG she has came from her work. So I'm going to take her 40 kilograms of mass, 9.8 Newton per kilogram for field, and 0.25 meters. So for each single pull-up that she does 40 times 9.8 times 0.25. For each single pull-up she does 98 joules of work. She does 98 joules of work, so let's put that in as positive. That adds energy to the Lucy Earth system. The applied force does positive work, so energy increases. But now let's talk about power. Power is work divided out by the time. And the work she does 10 pull-ups. So she actually does 10 of these 98 joule pull-ups. And she does that in 20 seconds. So think of this power as the total work she does. So she did 980 joules of work in 20 seconds. She's a crazy lady. This gives a power of 49 watts. Okay, so then part F, if she did the same pull-ups, she'd still be doing the same 980 joules of work. The work would be the same because she's still adding gravitational potential energy, but the time would change, so the power would change. By decreasing the time, she has to put out twice the amount of power. So instead of 49 watts, she'd be putting out twice as much power, so she'd be doing 98 watts. So the work stays the same because it's the same number of joules, but the power would increase. On to the last problem then. A tennis ball with a mass of 0.1 kilograms is thrown with an initial speed of 12. So let's do that kinetic energy. I know both its mass and velocity, so that's 1/2 times 0.1. V is 12, so 12 squared. So remember in your calculator when you do kinetic energy, do the 1/2 times 0.1 first. So that's 0.05. Then 12 squared is 144. Multiply those two together, so you like order of operations, make sure you do the right thing. So there's 7.2 joules of kinetic energy at A. Hey, while I have that, let's say I put 7.2 joules of kinetic energy at A, like right into here. 7.2. What about gravitational potential energy at A? PEG is mgh, so that's 0.1 kilograms times 9.8 newtons per kilogram times 15. Multiplied all together, and that gives us 14.7 joules. So at point A, I should be drawing about twice as much potential as it had kinetic. There's no elastic or spring energy in any of these pictures, A, B, or C. At B, though, it's higher up in the air, so I would expect even more gravitational potential. So maybe I draw this like a little bit higher. It is still moving at B. Check this picture. It is still moving at B, so I can get its kinetic energy. At point B, the kinetic energy is 1/2 mv squared, so that's 1/2 times 0.1 times 5 meters per second squared. Ooh, hard to find that. So the velocity at point B is 5 meters per second. So in my calculator, I'm going to do this in 2 steps. 0.1 times 1/2 is 0.05. 5 squared is 25. And then multiply these together. That's 1.25 joules of kinetic energy at B. So if you're thinking of like the steps of conservation of energy, now we are right there. Step 1, calculate all the energies you possibly can. We calculated the kinetic energy at A and B and the gravitational at A. That was all the information we could get. Now we're going to use that to calculate the total energy. Think of it like this. Since the total amount of energy in each picture has to remain the same, if there are 7.2 joules of kinetic and 14.7 joules of potential at A, that makes a total of 21.9 joules of total energy at B. All of the pieces have to have the same energy actually. So that must mean there are 21.9 joules of kinetic energy at C. And it looks like I did my math wrong here. Let's just check again for B. At point B, the total is equal to kinetic plus potential. Since the total has to equal 21.9, and I know there's 1.25 joules of kinetic, that must mean the potential energy left at point B is 21.9 minus 1.5, and let's check to make sure I get that number right. That's 20.65 joules of potential energy at B. Beautiful. So all in all, what makes it conservation of energy is the energy at A, B, and C are all equal to each other. Because there's no work being done by friction or external forces, if there's 21.9 joules of energy total at A, there must be 21.9 joules at B and 21.9 joules at C. Now, let's use them to find height and speed. So remember, anytime you want to find height in this unit, use PEG. It's the only equation with height right in it. Anytime you want to find speed in this unit, use K is equal to 1/2 mv squared. It's the only one with speed in it. Since I want the height at B, I'm going to take the potential energy at B. That's 20.65 equals 0.1 times 9.8 times h. For my order of operations, I'm going to multiply first. So that's 20.65 equals 0.98 h. Divide on both sides. So that h is equal to 21 meters. Let's call it 21.1 meters. 21.07? Close enough. All right, kinetic energy time. If I want a speed, I use kinetic energy. Since I want the speed at point C, I pick the kinetic energy at point C. Right? See, there's 3 kinetic energies. 7.2, 1.25, and 21.9. So let's do that. Is 1/2 mv squared, and solve for v. By order of operations, I'm going to take care of this multiplying first. That's 21.9 is equal to 0.05 v squared. Then divide on both sides, so v squared is equal to 21.9 over 0.05. And to take a square root, I'm going to hit power 0.5. This puts a final speed of 20.9 meters per second. I had someone ask me, they're like, wait, if that's 20 and that's 20 and that's 20, is it always true that potential is equal to the height, is equal to the speed? No, that's unfortunately a coincidence with this problem. But if you stick to this method, you'll be just fine. In this method, start by calculating all the energies that you have enough information for. Find the kinetic and potential energies. Then, set the energies in each picture equal to each other. The energy at A is equal to B is equal to C. Ooh, we'll fix that right now. It looks like I put this in the wrong column. We'll fix this on the final draft. Done. So all our energies should be equal to each other in all the pictures. Finally, find a missing height or speed. You'll be given all of these energies already, so if you want the height at B, you take the potential energy at B and solve for h. If you want the speed at C, you take the kinetic energy at C and solve for v. All right, everyone, good luck on your test tomorrow.